All right, so this video is part one of a series of videos that I'm going to put together introducing Ramsey theory. Now, Ramsey theory is named after Frank Ramsey, who died at the young age of 26. And he actually died the same year that he came out with a fundamental paper, which was called On a Problem in Formal Logic. It was in 1930. And in this paper, he had a result that he viewed more as a tool for disproving other results in logic. But the idea was that he argued that once something reached a certain size, he was able to guarantee the existence of certain predictable substructures. His work went relatively unnoticed for a bit of time before Greenwood and Gleason came out and really started developing the theory, and then later on the connections were made back to Frank Ramsey's work. Today, there's quite a few active branches of Ramsey theory, and what I'm going to focus on in this collection of videos is what I would call graph Ramsey theory. Now, that being said, before we get to graphs, there is a result that I would argue actually falls under the blanket of Ramsey theory that you're probably already familiar with, specifically the pigeonhole principle. So let's recall the general pigeonhole principle. If we start out with M objects and we have N compartments, and we're working under the assumption that M exceeds R times N, then we can guarantee that at least one of those compartments will have at least R plus one of the objects within it. And the way that we usually go about proving this is just by using contradiction. We suppose that this is false. Then of our N compartments, each one contains at most R objects. That means in total, there's at most R times N, and because M is assumed to exceed it, that gives us a contradiction. So it's a fairly straightforward result to prove just using contradiction. Now, graph Ramsey theory itself in most textbooks is usually introduced by a problem that was on the Putnam exam in 1953. And it's a very well-known problem, but I think it's a great starting point for us. So it's a question of how many people must be at a gathering to guarantee that there's either going to be three mutual acquaintances or three mutual strangers. Now, to take on this problem, one of the assumptions that we're making from the beginning is that there's a symmetry to knowing one another. If person A says that they know person B says they know person A. This isn't one directional where a person says they know somebody, but the other person has no idea who that person is. But one of the other things that we'll notice is for any given gathering, the more acquaintances there are, the fewer strangers and vice versa. So there's kind of a balance here. And it's not totally clear at first that there is a specific answer to this question, but because of that balance, we'll find that indeed there is an actual answer. Now, in starting this problem, let's go ahead and begin with the case of 5 people at a gathering. And we could represent those 5 people as vertices within a graph. And I have 2 colors here. And what I'm going to do is draw an edge between each pair of people and color that edge according to whether or not they know one another or they're strangers. Now, there's a lot of different possibilities, of course. There's going to be 10 possible edges here, and every one of them can be red or blue. That gives us 2 to the 10th possibilities. So there's a lot to check. But we can actually come up with a fairly straightforward example of a case where this does not occur. Specifically, imagine if the 5 people are sitting in a circle and everybody knows the person that's to their left and their right, but not the 2 people across from them. So I've colored those edges in red. So the red is going to represent 2 people knowing each other, 2 people being acquaintances. I'm going to use blue whenever 2 people are strangers. So basically this star in the middle ends up being blue. That's going to represent the cases of strangers. Now, if I'm looking for 3 mutual acquaintances or 3 mutual strangers, what I'm really looking for is a triangle that's entirely one of the 2 colors. And of course, notice there's no red triangle in this picture, and there's no blue triangle in this picture. So right away, just from this one example, that's all that we need to argue that 5 people are not enough. So if 5 people are not enough, that means it's necessary to have at least 6 to guarantee this, but it's not clear that 6 is sufficient yet. So we could take a similar approach. We could take 6 vertices and see if it's possible to start putting red and blue edges in them and do it in such a clever way as to avoid red and blue triangles. We're probably going to get pretty frustrated in this task because the answer actually does turn out to be 6. So we're not going to get very far. There's a whole lot of cases to check, and we're not going to want to spend all day going through and looking at them all. So instead, let's actually write a mathematical proof that 6 is sufficient to force this to happen. So let's consider a red-blue coloring of the edges of K6. Complete graph with 6 vertices. Let me draw K6 up here so we have it to look at. For the time being, I'm going to draw all my edges in white, but again, we're going to apply colors to all of them. So I've got my cycle going around. I'll go ahead and start connecting each vertex to everything it's not immediately next to. Got that one already. This one, this one, this one. Hopefully I'm not missing anything there. I don't think that takes care of it. Each one should have degree 5. So that's the interesting thing about this, is each vertex has degree 5. So let's go ahead and select one of these vertices. I'm going to select this one here, and I'm going to call it U. Now, U is incident with 5 edges, and those 5 edges are getting colored in red and blue. Well, because we're coloring them in red and blue, you could think of red and blue as being the 2 compartments, and then we have 5 objects that we're placing into those 2 compartments. No matter how you do it, from the pigeonhole principle, we know that one of those compartments is going to have at least 3 of the objects. So without loss of generality, I'm going to assume that it's the red compartment. I could back up at the end of this and prove everything focused on the blue compartment being the one that's chosen. The arguments are exactly the same. Without loss of generality, assume that U is incident with at least 3 red edges. I'm going to give those edges names. I'm going to call them UA, UB, and UC. So let me draw another picture to go along with this. So at this point, let me erase the rest of this. I don't really care about the entire graph anymore. I'm focused on the subgraph that's induced by the 4 vertices being mentioned here. So I have my vertex U, and I have 3 other vertices. And I have red edges going to each of those. These are A, B, and C. So now let's consider how A, B, and C are connected with one another. It's possible that AB could be red. If AB is red, notice that forces a red triangle, UAB. It's also possible that BC could be red. If BC is red, then UBC is a red triangle. It's also possible AC could be red, in which case UAC is a red triangle. So in all 3 of those cases, we're guaranteed to have a red triangle. The only other possibility is if all 3 of them are blue. And notice that's going to force ABC then to be a blue triangle. So that's our basic proof. So if any AB, BC, or AC are red, a red triangle is formed. Otherwise, the vertices A, B, C form a blue triangle. And that completes our proof. 6 is enough to force it. And 6 is the smallest number for which it occurs, because we can come up with one example on 5 where that doesn't happen. So this leads us to actually defining what a Ramsey number is. So let me give you that definition. So the Ramsey number is going to be denoted R of ST. So S and T are their arguments. This is the least natural number n, such that for every red-blue coloring the edges of Kn, there exists a red subgraph isomorphic Ks, or a blue subgraph isomorphic to Kt. So again, it's not totally obvious that this number is always going to exist for any arguments S and T that we plug in. But it does follow from Ramsey's theorem. In fact, we'll see a generalization in a later video where we'll prove that these numbers actually exist, but we'll do so by using a result of Greenwood and Gleason. And so let's kind of go through some of the first numbers that we call Ramsey numbers. So the simplest argument that we could start with is the number 1. So let's go ahead and take a look at 1 R of 1t. Now this, by definition, is the smallest natural number n, such that no matter how you color the edges in Kn, red and blue, you're guaranteed to either have a red K1 or a blue Kt. Well, what does it even mean to have a red K1? A K1 doesn't have any edges. So as soon as you have one vertex, you automatically have a red K1. So this one is going to end up being 1 for all t. We could also then take a look at R of 2t. And again, think about the definition of this. This is the smallest natural number n, such that no matter how you color the edges, red and blue in Kn, you're guaranteed to either have a red K2 or a blue Kt. Well, a red K2 is just a single red edge. So if we don't have any red edges, then we lack that. As soon as we have any red edge, that part's taken care of. So the only possibility is we're going to consider what happens if our Kn only has blue edges. Then the smallest number that's needed to guarantee a blue Kt is going to be t. And so this one ends up being equal to t. Now, the one that we just looked at, our main example that came from the Putnam exam in 1953, that was just the case of R of 3,3. This was the smallest number of people we needed at a gathering to guarantee either 3 mutual acquaintances or 3 mutual strangers. And we argued that 5 was not enough, but 6, it always happened, regardless of how we colored the edges red and blue. So this one is actually goes back to the work of Greenwood and Gleason. They did their work in 1955, and they developed a paper that you could really argue was sort of one of the foundational papers in graph Ramsey theory, but they were not familiar with Ramsey's work at all. Nowhere in their paper did they cite his work. They never used his theorem. In fact, they came up with a theorem of their own to argue that these numbers always existed. They certainly didn't call them Ramsey numbers. But they went through and they proved quite a few numbers. They proved RF33, RF34, RF44. Later on, we'll also take a look at a three-color Ramsey number, RF333. They proved that one as well. So they had quite a few results and did a lot to really develop some of the foundations of what we call graph Ramsey theory today.